So we've already looked at the first derivative test for finding extrema, minima, and maxima, and now we're going to look at the second derivative test, which will find the same sorts of things, but using the second derivative. So if we look at that, the idea behind the second derivative test is that we're going to use concavity to help us find the minima and the maxima. So at a critical point, if the function is concave up, remember this is concave up, kind of the smiley face, so if you've got concave up, then that means that this is where the critical point is, and so it's a maxima. So if the function is concave up, then that means it's, sorry, I think I said maxima, but it should be a minimum. Conversely, if it's concave down, or a frowny face, the critical point is at the top right here. And so if it's concave down, then that's going to be a maximum. And if the function has a, forgetting the name of it, if it has a point where the concavity changes, an inflection point, that's what we call it. So if it's got an inflection point at the critical point, then that means that there's neither. Because if you've got an inflection point, that means you're either doing something like this or something like this, which, clearly at the critical points here and here, you don't have a minimum or a maximum there. So let's look at an example of this. So find the local extrema for the function f of x is equal to x to the fifth minus 5x cubed. So what we need to do first is find our critical points. So the critical points we get by finding when the derivative is equal to 0. So the derivative of f prime of x is 5x to the fourth minus 3x squared. Set that equals 0, we can factor out an x squared, and then we're left with 5x squared minus 3. And so that gives us critical points at x equals 0 and plus or minus square root of 3 over 5, right? Did I make a mistake here? I did make a mistake here. So this shouldn't be 3, it should be 15. And that will let us factor out the 5. So let me go back. Here, 15x squared, which means we have x squared minus 3 and a 5x squared out here, plus or minus square root 3. So now we need to find the concavity at those points. So the second derivative of x is going to be equal to 20x to the third minus 30x, just 30x. Which, if you wanted to factor that, you could, but there's not really a need to. So let's go through and find f double prime of 0, because again, we're just looking for concave up, concave down, that sort of thing. Plugging in zeros, we get 0, so that means it's going to be an inflection point, or it's likely to be an inflection point, but that does mean it's neither a minimum or a maximum. F double prime of square root 3 is going to be, that will be a positive value because it'll be negative 30 square root 3 plus 20x cubed, which is going to be bigger, so it'll be positive. And then the second is negative, which is going to be negative. So I did that quickly mentally in my head of, negative number to the third, negative 20 something, negative 30 something, and 20 times square root of 3 to the third is going to be bigger than 30 times square root of 3. If you want to check that on a calculator, you can. But that ultimately means that we have a local minimum at square root 3, a local max at negative square root 3, and we don't actually know what's happening at 0, so we need to test further. So because it's 0, that tells us it could be an inflection point. We need to check to see if it is an inflection point. So if we plug in f double prime of -1, just to check a number to the negative side, we'll see that we get -1 to the third. That will give us a positive value. And f double prime of +1 will give us a negative value by the same token. So this is in fact an inflection point because we see that the concavity changed on either side. So that means that this is neither. Again, because it's an inflection point. And that's the idea behind the second derivative test. You find the critical points, you check if they're concave up or concave down, which will in turn tell you if they're local minima or maxima.